We have recently learnt about the representation methods of linear equations in two variables. We also know that these can be three possibilities. They will either intersect, be parallel or lie superimposed one over the other, if represented graphically. Now the question arises, can we reach a solution in each of the three cases? If yes, how could we achieve them? Our current topic helps to answer such questions. Here, we will find geometrically how to approach each of these three cases. For that, let us recall our three examples that we had covered earlier. In Arpita's fun park example, find out how many rides on the roller coaster Arpita had, and how many times she played shoot the balloon. Looking at the graph, we will notice that the pair of lines representing the situation in two variables x and y intersect at point 12, 4. This means that the point 12, 4 is a point common to both the lines, y equals x by 3, and y equals 60 minus 4 times x by 3, respectively. Algebraically speaking, this point should satisfy both the equations. Let us verify this by replacing the values individually for both the equations to find out whether the case holds true. For the first equations, LHS equals y, that is 4, RHS equals x by 3, which is 12 by 3, that is 4. Similarly, for second equation, LHS equals y, that is 4, RHS equals 60 minus 4 times 12 by 3, that is 4. Since LHS is same as RHS in both the equations with the values of x equals 12 and y equals 4, we can say it is a solution. Also, since we have only one point that is common, we can say, in this case there is one and only one solution for the given pair of linear equations in two variables. Thus, the number of rides Arpita had on the roller coaster is 12, and the number of games of shoot the balloon she played is 4. In the stationery shop situation of Naresh and Sonali, can you find the cost of each pencil and each drawing sheet? Looking at the graph, we recall that the pair of straight lines are overlapping or coincident, that is, they are superimposed one over the other on the graph. Now we know that the solution for a pair of linear equations is that common point that lies on both the equations. As in present case, all the points of falling on one line will be common with the second line. In fact, if we look closely, we will discover equation of one line is a multiple of the other, and thus both the lines are equivalent. Hence, there are infinitely many solutions to such pair of equations. For instance, we see that any point on the line gives us a possible cost of each pencil and drawing sheet. For instance, each pencil and drawing sheet can cost Rs 2 and Rs 7.50, respectively. Or, each pencil can cost Rs 6 and drawing sheet can cost Rs 4.50, and so on. In the situation involving two rods, can the paths represented by the two rods cross each other? Looking at the graph, we recall the situation geometrically represented as shown. It is very clear that the pair of rods represented by the straight lines have parallel paths. Hence, they do not cross each other. And, since they do not cross each other, they don't have a common solution. From the above three examples, we can conclude that the possibilities involving pair of linear equations in two variables can be summarized as: first, consistent pair of equations, that is, they have a unique solution, which is a point of intersection of the two lines. Second, inconsistent pair of equations, that is, they don't have a solution at all, since the lines are parallel. And third, dependent pair of equations, that is, they have infinitely many solutions, since the lines are coincident. Now, let us make a table for the three situations covered as examples for the pair of linear equations in two variables, and summarize them by relating the ratios of corresponding coefficients along with the geometric and algebraic interpretations. We will make use of the standard form for the pair for reference. In Arpita's example, the equations are as shown. The ratio of coefficients will be as shown. On comparing, we find that A1 by A2 is not equal to B1 by B2. On graph, these are intersecting lines. Algebraically, they have exactly one unique solution. In stationery shop example, the equations are as shown. The ratio of coefficients will be as shown. On comparing, we find that A1 by A2 is equal to B1 by B2, which is also equal to C1 by C2. On graph, these are overlapping coincident lines. Algebraically, they have infinitely many solutions. At last, the two rods example, the equations are as shown. The ratio of coefficients will be as shown. On comparing, we find that A1 by A2 is equal to B1 by B2, and these are not equal to C1 by C2. On graph, these are parallel lines. Algebraically, they don't have a solution. Hence, if the lines are represented by the general form A1x plus B1y plus C1 equals to 0, and A2x plus B2y plus C2 equals to 0, then these are intersecting when A1 by A2 is not equal to B1 by B2. Coincident when A1 by A2 is equal to B1 by B2 is equal to C1 by C2. And parallel when A1 by A2 is equal to B1 by B2 not equal to C1 by C2. Converse of the above is also true when we first find the ratios, and then predict if the lines are intersecting, coincident or parallel. Let us now move to the next section where we will solve some more examples to illustrate the learnings. Please pause the video, rewind and play again to absorb what has been covered in the topic. Let us proceed now.